Welcome to Chemistry at Honeyniga High School. I'm Brian Brown, and today we'll be looking at our second set of notes over Chapter 14. And today we'll be looking at the relationship between gas law variables. In particular, we're going to be looking at what we call direct versus inverse proportionality, because we'll notice that in some situations when we look at our gas law variables, they're what we call directly proportional, and other times they're inversely proportional to each other. And that has mathematical implications as to the math that we're going to see with these various gas laws. Now, the one we're going to talk about today is basically Boyle's law. And Boyle's law deals with the relationship between the two variables, pressure and volume. And what Boyle found was that at constant temperature and amount of substance, so constant mass, the pressure was inversely proportional to the volume. Now, one of the things I want you to have a better understanding of is what it really means to be a direct versus an inverse proportionality, and how that statement is determined, and how mathematically it becomes an equation like this. So if pressure and volume are inversely proportional, then we can say P1V1 equals P2V2. Now the ones would represent initial conditions, and the two would represent secondary or final conditions. So if we had a initial pressure and volume and a new pressure, we could calculate the new volume V2. Well, where does that law come from? And what does that have to do with direct versus inverse proportionality? And how do scientists determine those things? Well, it really starts with graphing the variables. So if we take a cylinder and we measure its pressure at a certain volume, then we change its volume and measure the new pressure, change its volume again and measure a new pressure, we end up with a graph that you see over here. Now, it's a nice looking graph, but the problem is it's not a linear relationship. So the relationship between pressure and volume is not a nice linear one. And the reason linear is important is because linear is a constant slope situation, which means there's mathematical implications to a linear situation that are easy to look at and understand. So in this particular case, it wasn't pressure versus volume that's linear. So what we really need to understand is how we have a graph like this, pressure versus volume, not linear. What do we do, and how does that give us an inverse proportionality? Well, what we do is we graph one versus the inverse of the other next. So we're going to take our same volumes, and now we're going to graph it versus the inverse of the pressure. So literally, I just take the reciprocal of every pressure at each volume, and I graph what that looks like. And notice magically now it is a linear relationship. Now, the reason linear relationships are so important is they have a constant slope. So slope is rise over 1, so this would be v over the inverse of p that was linear. So p versus v is not linear. It's not a constant slope situation. Therefore, this relationship, v over p equals constant, well, that's not true. But in this particular case, since the inverse of p versus v was linear and it has a constant slope, that means this relationship is true and valid. The volume versus the inverse of the pressure equals a constant K. Now, the reason why this K doesn't appear in the equation that we're going to see is it's not a universal constant. Every temperature, we would have a different K. At every amount of gas, different numbers of moles, we would have a different K. So the K is not as important as the relationship that volume versus inverse proportionality actually equals a constant. And as long as we're not changing the temperature and the number of moles, it's going to be the same constant, and we can exploit that. Now, in terms of a mathematical statement, when something is inversely proportional, we would write it like this. And this fundamentally means the volume is proportional to the inverse of the pressure. And mathematically, that becomes this. The volume equals K times the inverse of P. And this is really just rearranging the equation we looked at a second ago. Now let's take a closer look at that equation. Now, we're not quite to what Boyle's law is, but notice we've got volume on one side, K on the other, and inverse pressure on the other. Well, if we multiply both sides by pressure, what we're going to end up with is this. P times V equals K. Now we're starting to look closer to what we saw as the equation for Boyle's law. So that means at some initial conditions, P and V, P times V equals K. And as long as I don't change the temperature and the number of moles, at a new volume, I'm going to get a new pressure, but they're still going to multiply to the same old K. And that then means that P1V1 has to equal P2V2 as long as we don't change our temperature or our number of moles. And that's where Boyle's law comes from. So it's an inverse proportionality, and mathematically, this is how we use it in problems. So if we have a pressure and volume and go to a new pressure, we can calculate the new volume. If we know a pressure and volume and we go to a new volume, we can calculate the new pressure using this equation. So that is what we call Boyle's law. Now, when we go to do any of our gas law problems, we're going to follow a four-step process. The first thing I always want you to do is read the word problem, and I want you to set up a variable table. Now, when you plug in your variables, remember we got ones and twos. Those are at the beginning and at the end, initial and final, first and second conditions. But the one thing to watch out for when you're putting those variables in the variable table is, do we have consistent and appropriate units? So if one pressure was in atmospheres and the other pressure was in kilopascals, mathematically we can't use P1 V1 if the units are different. So we would have to convert to a common unit. One of the biggest ones you might see is something like milliliters and liters. So it's easy because we've done it several times before. If we know milliliters, we can divide by 1,000 and we can get liters. If we know liters, we can multiply by 1,000 and we can get milliliters. So they just have to be consistent. Now, appropriate, the single biggest thing you're going to see with appropriate is typically this one. We measure temperatures in the lab in degrees Celsius, but mathematically we have to be in Kelvin. The Kelvin scale is the only scale that's truly proportional to the speeds of the molecules. At 0 Kelvin, molecular motion would have stopped. So when we do these mathematical expressions for the different gas laws, we always have to have temperature in Kelvin. And consistently in problems, it's going to be given in degrees Celsius. So that's something we're going to have to be aware of. Not for Boyle's law, because there's no temperature. It was constant temperature in that situation. Second thing I want you to do is I want you to write down the equation we're going to use. In the case of Boyle's law, we would write down we're going to use P1 V1 equals P2 V2. And that way you're establishing to me, do you understand the relationship between the variables? The third thing I want you to do is I want you to solve this equation with the variables. Not by plugging in numbers. I want you to mathematically manipulate this equation before you plug in numbers. And that's going to be worth points on the test and points in the homework. So for this particular case, let's say we didn't know V2. So we want to solve for V2. Well, V2 has to be on top. It already is. And it has to be alone. So if we divide both sides by V2, we would end up solving for, I'm sorry, divide both sides by P2, we would end up solving for V2. So my base equation is P1 V1 equals P2 V2. When I solve this equation mathematically for V2, what I'm going to end up doing is this. And what I'm going to be left with is V2 is going to equal P1 V1 over P2. And that's something I want you to do every single time you use an equation in this chapter, is solve it for variables. And it's not optional. You have to do it. You need to get good at this algebra. And then finally, you plug in your numbers and then round to correct sig figs with correct units. And when you're plugging in your numbers into this equation, make sure you write them with correct units so you can see, do they cancel to give you the appropriate unit for the appropriate problem? Always include your units in your work and cancel them to see what you get. So when you go to do the Boyle's Law worksheet today, that's what I want you to be using. Now, how does that look as a problem? So here's a typical Boyle's Law problem. A balloon contains 30.0 liters of helium gas at 103 kPa. What is the volume when it rises to an altitude where the pressure is only 25.0 kPa? Assume the temperature is constant. Now, it's not mentioned, but the other thing we can assume here is it's a sealed balloon, and our number of moles of gas is not changing as well. So first, what equation are we using? Well, this is pressure volume. That's Boyle's law. We looked at that was P1 V1 equals P2 V2. So we need pressures and volumes in our variable table here. So what was my initial pressure? Well, that was 103 kPa. What was my initial volume? That was 30.0 liters. What was my final pressure? Well, that was 25.0. What was my final volume? Well, I don't know. That's the purpose of the question. And the equation I'm going to use to solve this relationship between pressure volume is Boyle's law. P1 V1 equals P2 V2. Now, what I want to do next, after I've established this equation, is solve that equation for variables. Don't plug in your numbers yet. First, solve it for variables. And we just looked at it a second ago. If we divide both sides by P2, V2 will end up on top and alone, and therefore we've isolated the variable. And V2 would equal P1 V1 over P2. Doing that mathematically is always going to be worth points. Next, we plug in our numbers in our appropriate places. We've already got a variable table set up. We know where things are supposed to go. Plug them in, and at that point, multiply it in the calculator and divide in the calculator. Everything on top multiplied, everything on the bottom divided, hit equals, and you'll get an answer. But remember, we have to round to appropriate sig figs. So my three numbers, 103, 30.0, and 25.0, all have three significant digits. Since I'm multiplying and dividing, I'm stuck with three sig figs in my answer, and I get 124 liters. And that ends our notes over Boyle's law.